All right, let's start out with some definitions. So this is a kind of a continuation of the same unit we were on. It's more probability stuff. We're going to look at probability distributions of random variables. So the first thing I want to define for you is what is a random variable. So get ready to write. It's a numerical value. So it's a number that describes the outcomes of a random process. Describes the outcomes of a random process. So it's a number. Like if you're flipping a coin, the outcomes that now are not going to be heads and tails. It's going to be some kind of a number value. All right. And we're going to be looking at probability distributions throughout this chapter. So what is that? A probability distribution gives possible values of the variable. It gives possible values of the variable and their probabilities. It tells you all the possible outcomes and the probability of that outcome happening. If you just kind of look in the middle of your page, this little table right here, that's what a probability distribution table looks like. It just tells you all the possible outcomes, and we'll look at this in just a second, but the number of languages a student speaks, and then the probability that if I draw a student at random, that they speak this many languages. That's all a probability distribution is. And then we need to talk about, we're going to talk today about the difference between discrete and continuous variables. You've been exposed to that vocabulary prior to this class. You've been exposed to that vocabulary in this class. Discrete means that it's a random variable with gaps between variables. A random variable with gaps between values. Usually things that are counted. Be like shoe size. Now shoe size, you might be thinking, well, there are half sizes. Yes, you can have a shoe size 5.5, 6, 6.5, 7, but that's still discrete because there aren't any in between those. Shoe size, number of students in a class, etc. Usually things that are counted. There are gaps between the values. That's discrete. We're going to look at a discrete random variable now, a probability distribution, and kind of learn how to read these. I think you'll find this is pretty straightforward. Imagine selecting a U.S. high school student at random. Let X be the number of languages spoken by the randomly selected student. The table gives the probability distribution of X. So that's what a probability distribution looks like. Part A says, why is X a discrete random variable? And we're just going to write because you either speak 1 or 2 or 3, etc. languages. You either speak 1 or 2 or 3 ... languages. There are gaps between values. That's why it's discrete. We kind of touched on this before. This should feel kind of familiar. If you're asked, like, is this a legitimate probability distribution, or prove that it works, just glance at your probabilities. All of those probabilities should be between 0 and 1, and they should all have a sum of 1. They should add up to one whole. So if you want to put equals 1 on that bottom row, just to remind yourself. If we actually grabbed our calculators and added those together, we would see that they do equal 1. So where it says show that the probability distribution is legitimate, you can just write all probabilities are between 0 and 1, and the sum is 1. So just check for those two things. We haven't done this next part in a while, making a histogram. So let's see if we can crank one of these out. Just draw your two axes and our possible values for x for number of languages. 1, 2, 3, 4, 5. We're going to label that number of languages. And we're going to put the probability on the y-axis starting at 0. And it looks like the highest number that I need to go up to if I'm looking at my y values here is 0.63, so maybe I want to go to like 0.7 just to cover all my bases. And I'm going to put probability and then 1, 2, 3, 4, 5, 6. Okay, now histogram. I haven't seen these in a while. The bars are going to be touching, but listen really closely. Because we're dealing with a discrete random variable, you're going to actually center the bar. Like I'm going to center the bar for 1. I'm going to go up to 0.630, but I'm going to center the bar over that value of 1. Histograms typically show a range of values, but because these are discrete, this single bar right here shows the probability for a student speaking exactly one language. Not like anywhere from 1 to 2, but exactly 1. So center it over the values. All right, the probability that I pick a student at random and they speak 2 languages is about 0.3, almost 0.3. 3 languages is 0.07. And then it just gets smaller from there. 0.008. 0.002. So the probability gets smaller and smaller that a student speaks more and more languages. It says to describe the shape. So just to make sure we kind of remember these things. The shape is definitely, I would say, strongly skewed. Which direction? The way the tail goes is to the right. Very good. So shape, we would probably say unimodal, strongly skewed right. When I was looking over these notes this morning, we're going to kind of talk about this again in just a second, but before we leave this picture, do you remember in a strongly skewed right graph, what's going to be bigger, the mean or the median? Do you remember those things? Which one of those two things gets pulled towards the tail, the mean or the median? The mean, because the mean is not resistant. So if the mean gets pulled towards the tail, that means that the mean is going to be slightly larger than the median. And we're going to discover that kind of in the work that we do with this, this foreign languages example here in just a second. So let's see if we can just kind of use some intuition on part C. It says, what's the probability that a randomly selected student speaks at least 3 languages? A lot of you could do this on your own without me showing you how, but I want you to be able to write that in symbols. So look how I write this. I want to know the probability that X, which represents the number of languages, that capital X, is at least 3. So what symbol would I use for at least 3? Would it be less than, greater than, less than equal to, greater than equal to? Greater than or equal to 3 is how I would write it in symbols. And look back at that table up there. What do you think you're going to do? It's really easy, you guys. Yeah, you're just going to add the probabilities that a student speaks 3 or 4 or 5 languages together. You're just going to add, if you want to show a tad bit of work here, you're going to add 0.065 to 0.008 to 0.002, 0.65 plus 0.08 plus 0.02, and you get 0.075. That's the probability that a randomly selected student speaks at least 3 languages. That's 3 or more. Now it says interpret that probability. Probability means in the long run. So I want to revisit this concept with you where we kind of write the phrase many, many times. And so here's what this means. If many, many high school students are selected at random, and I guess technically U.S. high school students, if many, many high school students are selected at random, there's about a 0.075 probability that one randomly selected student speaks 3 or more languages. Or you could put at least 3. This means over a whole bunch, a large number. It's that law of large counts. It doesn't necessarily mean in this tiny little class of 9 people that if I select a person at random that there's a 0.075 chance that people in this small group speak 3 or more languages. It's over a giant number. Okay? Let's see how that's different than the next question, the way this is worded. What's the probability that a randomly selected student speaks more than 3? The last one said at least 3. This says more than 3. So now I want to know the probability that x is, what's the difference? Just greater than 3. Very good. So that just means leave out the 0.065. And I copied it and pasted it here for you so you don't have to flip back. So we're just adding the 4 and the 5 probabilities together. And I think I have it written incorrectly in the Schoology notes. I have 0.1 in there, but it's 0.01. And it just says, how is that different? More than 3 does not include 3. That phrase, more than 3, doesn't include 3. So just be careful with your wording. The math should be pretty easy. Just pay really close attention. Okay, we're going to look at something that at first glance can be very intimidating, but I promise what I'm about to show you is not difficult. You just have to trust me a little bit, okay? And I'm going to do the math teacher thing where I explain it, and then I kind of just tell you what you need to know. It says imagine, okay, so here's the same scenario. Find mu of x, also called the expected value. You might see this symbol here, capital E of x, the expected value. Remember that mu stands for the mean or average. So first things first, I want you to know that these terms are interchangeable. If I tell you to find the average or mean number of languages spoken, or if I tell you to find the expected number of languages spoken, mathematically, those are the same thing, okay? So let's put E of X equals, and this is how you find it. Well, I'll revisit this, how to read this in just a second, but let me kind of show you what you would do, okay? To make our math really easy, let's say that 1,000 students are looked at, okay? 1,000 students. And the reason I'm choosing 1,000 is, look what I'm pointing to, these decimals happen to go out to the thousands place, okay? Tenths, hundredths, thousandths. So just to make our math easy, let's say we have 1,000 students. That means that 630 of them would speak one language. 295 of them would speak 2 languages, 65 of them would speak 3, 8 of them would speak 4 languages, and only 2 of those 1,000 students would speak 5 languages, okay? So let's kind of write this down in words. To make the math easy, let's say that 1,000 students are selected. What that would mean is that 630 would speak one language. Don't worry, we're not going to write all of it. 295 would speak 2 languages, and then just put dot, 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 etc. So I chose 1,000 because the decimals go out to thousandths. Now I'm trying to find the average number of languages that are spoken out of these 1,000 students. So the average, that's what mean is, that's what the expected value is. To find an average, you add everything together and then you divide by how many there are. So the average would be, it would look something like this. Okay, I would take one student. They speak one language. And then there's another student who speaks one language. And there's another student who speaks one language. There are 630 of those. And then I get to the students that speak 2 languages. There are 295 of those. And then I get to the students that speak 3 languages. Remember, we have to add all the numbers together and divide by however many there are. There's 65 students that speak 3 languages. And then I get to the ones that speak 4 languages. There's only 8 of those. And there's only 2 who speak 5. I would have to add all 1,000 of those values together and then divide by, put a big old slash bar there, and then I would divide by 1,000. Add them all up, divide by however many there are. You learned how to find averages of things when you were little. Here's another way to write that. 1 times 630 plus 2 times 295 plus 3 times 65 plus 4 times 8 plus 5 times 2, all divided by 1,000. And lastly, here is where the math teacher in me is finally going with you guys. Instead of dividing at the end by 1,000, you could just change these decimals to thousandths. So this is the same exact thing as 1 times 0.630 plus 2 times 0.295. Look at that table. Plus 3 times 0.065 plus 4 times 0.008 plus 5 times 0.002. So all you really have to do, the purple stuff that I wrote there at the very end, check this out. If you're ever asked to find the mean and you have a little table, just multiply the value of x times its probability and add that to this one times its probability added to this times its probability. And you guys, that's all this says right here, is it's the sum of a value times its probability. That big scary formula, that giant sigma, just means add together every value multiplied by its probability. And I want you to go ahead and put what we would actually get in this foreign language problem is 1.457. Now let's figure out what the heck that really means. What did we just find when we sat there and we found the sum of every value times its probability? What does that mean? What is the expected value? What is mu? Well, that means if we randomly selected many U.S. high school students, they would speak about 1.457 languages on average. That's what that means. So here we go. If we selected many U.S. high school students, they would speak, and when we found the average of them, they would speak about 1.457 languages on average. It sounds funky to say 1.457 languages because we just talked about the fact that this is a discrete value. So I'm going to address that in this next question that sounds kind of weird. But it says, does the expected value or the average that you found have to equal one of the possible values? In other words, do I have to get 1 or 2 or 3 or 4 or 5 languages? Should we round to the nearest integer? Should I round that to just one language? What should I do? Well, since probability means in the long run, you don't round. You don't have to get a discrete answer just because we're dealing with discrete values. So just put no, because you should think about the mean in the long run. No need to round. So that 1.457 is good as is because we're talking about the mean being the long run average. Over a whole bunch of people, that's the average number of languages they speak. All right, let's go to page 3. You are going to have to do this, I think, on a couple of your homework problems, and I'm going to help you with your homework today, just kind of how I have been. But it says to construct a cumulative probability distribution of x, and we haven't done that in a while. Cumulative just means like a sum, and use it to calculate the median. We talked about that histogram and how the median is going to be smaller than the mean because it was really skewed right. Well, what we just found on the previous page was the average, 1.457. So we should get a number smaller than that here. How does it compare to the mean, and why should this be expected? Okay, so here we have that number of languages and their probabilities. The cumulative part just means this, okay? You're going to just add up the probabilities as you go. So we're going to start with 0.630, and then we're going to add 0.295 to that. 0.630 plus 0.295 gives us a cumulative of 0.925. And then we're going to add 0.065. That brings us up to 0.99. And then we're going to add 0.008, which is going to be 0.998. And then you should always get to one whole at the end of your cumulative probability. And that was those graphs that kind of looked like this, where they would go up up to one whole. And we had to graph them. But you don't have to graph this one, you just have to complete the probability distribution with that cumulative row. All right. So how do we figure out the median? Well, the median is at the 50th percentile. So look for the first cell in the table that breaks 0.5. That's how you'll always do this type of problem, is you'll just look across like our red numbers here and look for the first cell that's higher than 0.5. Now this is kind of a lousy example because it's right here. That 0.630, that's the first cell that breaks 0.5. When we look at a homework problem together, you'll see that, you'll see a little bit better of an example. That means this, the median number of languages spoken for a whole bunch of high school students is 1. That's the median. So just look for the cell that breaks 0.5, look at the value that corresponds to that, that is the median. So write this sentence. The median is 1, which is smaller than the average, which was 1.457. This is expected because the distribution is skewed right. Anytime you have a distribution that's skewed to the right, the mean is going to be larger than the median. The median is going to be smaller than the mean. So in the previous page, I showed you how to find the mean. Right here, I'm showing you the pretty simple way to find the median. And now we're going to talk about variance and standard deviation. Again, I know that these formulas look completely crazy and intimidating, but don't be too worried. I'm going to show you eventually how to do these in the calculator, but here's the catch. You have to show at least your first few values, like on the AP exam. You have to show work for like the first few parts, and then you can just grab your calculator to get the final answer. So you will have to kind of know how to read this for variance and standard deviation. Now the beauty of this is these are on your formula sheet. You don't have to memorize those, that would be crazy. But you'll have to show a little bit of work for the first few terms, and then you can just put a dot, 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 and put your answer. I'll show you how to do these in the calculator. All right. So here is that number of languages again. We're kind of sticking with that as our example throughout these notes. Calculate and interpret the standard deviation of x. So usually, anytime we're asked to find a mean, its cousin is standard deviation. The measure of center is mean, and the measure of variability is standard deviation. Okay. So here's how, according to this crazy formula up here, here's how we find standard deviation of the number of languages spoken. We have to take this formula right here. I'm going to copy that formula down so we can see that it's really not that scary. We have to find the sum of each value, how far away each value is from the mean. And then we're going to square that, and we're going to multiply it by its probability. So every single value minus the mean, that deviation, we're going to square it, we're going to multiply it by the probability, we're going to add all those together, and then we're going to take the square root. Holy moly, that's a lot. So watch what this looks like in this particular example. I'm going to take this first value, which is one language spoken. I'm going to see how far away that is from the mean. Well, the mean that we found on page 2 of the notes was 1.457. That's the average number of languages spoken. Then I'm going to square that value, and I'm going to multiply it by, look what I'm pointing to. I'm going to multiply it by the probability that corresponds with that value, which is 0.630. Then I'm going to add that to the next value, which is 2 languages spoken. I'm going to see how far away that is from the average of 1.457. When I say see how far away it is from, that's why I'm subtracting. I'm finding the difference. I've got to square whatever that is and multiply it by its probability, which is 0.295. Now, here is where you're allowed to just put a ... on the AP exam. You're going to show at least the first couple of terms, the work. Don't forget to put a square root over it. If you didn't put a square root over it, then that would be you finding the variance, but this says find the standard deviation. Variance is just standard deviation squared. Okay, we'll come back to this. I'll help you actually find that in the calculator because that's the next part of the note. So just put an equal sign and we'll come and put the answer in just a second. How do you use your calculator to find the mean and standard deviation? Okay, thank goodness we get to use a calculator to do this. But you're going to enter your data into list 1 and list 2. You're going to enter your data into list 1 and list 2, and then you're going to hit stat. You're going to go to calc, and you're going to do 1 bar stats. You're going to make sure where it says list, you have list 1, and then we haven't done this before, frequency list, you're going to make sure is list 2. And delete when you're done. Be patient with me. Go ahead and copy down these steps. And the reason we just want to delete that when you're done is because, well, it's just kind of good calculator habits. But oftentimes you don't really need that there. You just kind of have to know what you're doing in the calculator. If you enter things into list 1 and list 2, then you want list 2 there. If not, then you just delete it. So let's try now with this number of languages and the probability. Let's see if we can get our calculator to tell us the mean and the standard deviation. Here we go. Stat, edit. If you're like me and you've got a bunch of values there that you need to get rid of, run out of batteries. Clear out those lists by highlighting the header and hitting clear enter. Or you could always reset the memory if you want to. Let's enter in our number of languages, 1, 2, 3, 4, 5, and their probabilities. Oops. Once you have your probability distribution table entered, then hit stat, calc. We've done the one variable statistics before, but this time, okay, before we didn't have this list 2 here, but now we need to make sure that there's a list 2 there. So if you don't have a list 2 sitting right there, here's how you get it, okay? The word list is in blue right above the stat button, so hit second stat. Anytime you want to swap a list out for another one, this is how you do it. Just hit second stat and make sure list 2 is your frequency list. That's it. Enter, enter, and check it out. Your calculator is going to call Your calculator is going to call this X bar. But there it is. That's what we calculated by hand on the previous page, 1.457. And then the standard deviation is going to be, your calculator is going to call the standard deviation exactly what it is. So that's this 0.671. So let's go back up here and put 0.671. So I want to just reinforce to you that you can find these in the calculator. You're looking for X bar and sigma X, but you have to do this much work. Like, you have to show this on a free response to get full credit. You have to show that you're using the appropriate formula and you're plugging into it and you have some understanding, okay? All right. So everything I've shown you thus far has been about discrete variables. Now we're going to see how we deal with continuous variables on the last page of the notes. So all of that was about discrete. Well, what is continuous, and give some examples. Continuous means that you can take on any value in an interval on the number line. Can take on any value on a number line. It's usually things that are measured. So whereas before discrete was counted things, usually these are measured. I don't really care if you want to give some examples or not, but just, look for units like things that are measured. So inches, centimeters, feet, miles per hour, rates of things, those would all be continuous. And this next question is really funky. It says, is it possible to have a shoe size of 8? Yeah, yes for shoe size. So that would be discrete. Is it possible to have a foot length of 8 inches? And you might be thinking, well, yeah, but it's unlikely, believe it or not. Unlikely for foot length. And here's why. 8 inches means exactly 8. We could keep going and going and going and going. It's very unlikely that you would have exactly 8 inches for your foot length. So foot length would be one that we would consider to be continuous. Again, it's measured in inches. That's an easy way to tell that it's continuous. Well, I'm going to build on that concept. So how many possible foot lengths are there? Well, that would mean that they're infinite. There are infinite foot lengths, technically. So how could I graph a probability distribution of something that's infinite? It would be a histogram with an infinite number of skinny bars. And I'll draw you a picture in just a second. A histogram with an infinite number of skinny bars whose areas add to 1. And what that's going to create, I'll show you a picture, is that is going to create a density curve. So here's how I would draw this. Bunch of skinny little bars kind of creating a bell curve. And you don't have to draw this if you don't want to. I think it's very interesting though. And this happens again because there are an infinite number of foot lengths. So we have to be considerate of all of the in-between values. And that's why we end up just kind of estimating it with a density curve. And density curves always have an area of 1 underneath them. So these bars would have an area to add to them. Now I kind of hope you have some insight on where we're headed with this. Anytime we see this normal distribution shape, we're going to probably end up drawing pictures, shading to the left or to the right of values, and using normal CDF or inverse norm. So let's bring in that old knowledge here. How do we find probabilities for continuous random variables? It's the probability is the area under the curve above the values that make up the event. And just remember that the area under the whole curve is 1. So what I mean is, if you want to draw a teeny tiny little picture here, if I call that value A, and I want to shade to the left of it, because in my word problem it gives me some indication that I'm looking for that value or less than that. That shaded area right there is the probability that the value is less than A. That's when you would do normal CDF. Your lower would be -1,000. Your upper would be whatever value A is in the problem, and you would get your probability. It's the same thing you've done before, but now we're just assigning a probability to it instead of just an area. Okay, something that's really important for you to understand here is with a continuous variable, there is no difference in these symbols. There's no difference between less than and less than equal to. Now, when we were talking about the foreign language problem, how many languages a student speaks, there was a difference between whether we include something or not. It was that at least 3 versus more than 3. But with the continuous variable, those mean the same thing. They are the same because the boundary line adds no value. Think about this little these skinny bars right here. There are so many of them that they're basically just lines. And so including that little teeny tiny line or not doesn't change the value. So because the boundary line adds no value, it's infinitely small. It's like a histogram bar that's infinitely small. But just remember that this is not true for discrete random variables. There is a difference between whether a value is included or not when we're talking about discrete values. So always just at the beginning of a problem, ask yourself, is this discrete or continuous? Is there going to be a distinguishable difference between these symbols or not? So there's only one example for these because we've done it before. Check this out. This should feel like riding a bike. The weights of 3-year-old females closely follow a normal distribution. Here's the mean weight of a 3-year-old female, 30.7 pounds, and the standard deviation is 3.6 pounds. Randomly choose one 3-year-old female and call her weight X, capital X. Find the probability that the randomly selected 3-year-old female weighs at least 30 pounds. So we want the probability that she weighs at least 30, which is 30 or more. let's draw a picture of this normal distribution curve. The mean weight is 30.7. I want to know the probability that she weighs at least 30. 30 is somewhere over here. And I want to shade to the right because it says at least 30. So here's where 30 is located. It's just slightly to the left of 30.7. I want to know the probability that her weight is somewhere in the shaded region here. So all you need to do is normal CDF. Lower is the weight of 30, like that A that I showed you up here. Okay. Upper is going to be 1,000. The mean was given 30.7, and the standard deviation was given 3.6. Cram that all on there. Grab your calculator. See what you get. Where do you find the normal CDF function in the calculator again? Second bars, good. Just want to know the probability when I'm given the average and the standard deviation. I want to know the probability that I grab at random a 3-year-old female and she weighs at least 30 pounds, 30 or more pounds. And it looks like I'm getting about 0.577. Let's write a sentence. The probability that a randomly selected 3-year-old female is at least 30 pounds is about 0.577. The probability that a randomly selected 3-year-old female weighs at least 30 pounds is about 0.577. So continuous random variables actually should feel a lot easier to deal with than that discrete, because the discrete ones are where you have to use those crazy formulas to find your mean and your standard deviation. Now technically part B, you've seen problems like this before, you just haven't seen this notation. Let's figure out what it's asking us. If the probability that a female's weight is less than K is 0.8, then find K. So here's all it means. Same scenario about these 3-year-old females, where we've got 30.7 as the average. Okay, look right here. The probability that her weight is less than some number is 0.8. Well, 0.8 is going to be over here. That's like the 80th percentile. I knew to shade to the left because the symbol was less than. Shaded to the left. Because it said less than. If it had said greater than, I would have shaded to the right of that value. You remember how this one we were given the value and we needed to find the shaded area? Now we are given the shaded area as 0.8. How do we find the value? There you go, that's the inverse norm. And if you're like, okay, I kind of remember that, but I don't remember what the calculator needs, well, go to inverse norm, second bar is inverse norm, and it'll just kind of guide you on what you need. Area, do you remember the really specific thing about area? It's always the area to the left, and in this case, that's not tricky because it told us the area to the left is 0.8. If it had told us that the area to the right was 0.2, then we would have to subtract that to know that the area to the left was 0.8. But this is very straightforward, and then you get to just type in the mean and the standard deviation that are given to you in the problem. That's why this last little page of notes for continuous random variables was just 1 out of 4 pages of notes. So what we just found is this would be like the weight at the 80th percentile, if you want to think of it that way. K is 33.73. Area is 0.8. The mean is 30.7. The standard deviation is 3.6. And we get 33.73 pounds. Again, if you want to just add something extra to tie in old information to what we're doing now, that would be the weight at the 80th percentile. So with continuous, you use these bell curves. With discrete, you're going to have to do some calculation. And that pretty much wraps it up.